How can I do that? Yes. So. Okay. So welcome back. So last week we had a really interesting holidays because of typhoon. Okay, and the weather was quite nice, right? But we don't have any time for another week to finish review 2 and review 3 all together because I have just set 16th of October, right? October will be our first midterm, right? So we will be next week, right? Next week, next Wednesday. And thanks to TA, teaching assistant, he managed to book classrooms in engineering building 5 rather than here because I have received many complaints from your senior last few years. They had their midterms here and then they just cursed me because their back were really not really comfortable because they're just kind of bending for 3 hours. So the reason why this is the reason why I asked teaching assistant to book the classrooms in engineering building 5. So please tell everyone you know, okay? And there will be an announcement in our Facebook and E3. So please take care of, be really careful about the announcement. Okay, thank you. And also, I would like to, and then I would like to go through really quick for the last week because last week should be in the video, right? Video teaching. So I will just give a really quick summary that what we finished the last few weeks. And I have done this. Review 2. Writing 2. Okay. So last time I remember I finished around here, right? Okay. So just talk about how the entropy change for ideal gas. I guess I finished here. And then from here, it will be it was video teaching. So typically TDS equations are really important that connecting different parameters T, V, P to entropy. So they are really useful. And why they are really useful because these five reasons here. Okay, and this is the proof that TDS equation 1 can be valid. And this is just some calculations. And then equation 2 is also from similar behavior. We just do the calculation. And then the third relationship for CP minus CV is actually combine two TDS equation together, make it equal. And then we can have the conclusion CP minus CV equal to something in the right-hand side. Okay, and this is useful for calculate CV of a solid. And this is really useful because all the right-hand side are material properties. And CP is easier for us to measure in experiment. So CV can be directly, straightforwardly calculated by these equations. And then this is an example. And a free expansion of an ideal gas is that this is a trick that we're using the behavior of state function of S, right? So normally it is difficult to determine the delta S irreversible, but if we just using the trick that the final points has similar S, we can just make another reversible isothermal process which can identify which has identical final point for the S, so we can determine the equivalent delta S, and then we just do another entropy change, because entropy change needs the integration. So we just we show how to do the integration tiers. Okay, so this is review 2. And the beginning of the review 3 is that some useful mathematics techniques. And this is Legendre transformation, and we will use that later in this class. And you can find that there is sort of changing the parameters, changing variables of the function. And also you may notice that after we done the introductions, you see we have chapter A table, right? Table in chapter A. This is kind of big one, and I guess most of you familiar with that. How they determine that, because we can use the Legendre transformation to make them all connected and swap. Okay, the relationship can be swapped. So here is a swap both of the parameters, and here just swap one parameters, but really similar. And we have done some mathematical trick that we can get rid of undesirable constants and also a change variable. And then implicit dependencies. We also can find that the underlying connection between each parameters. Okay, so this is the third review, which is corresponding to chapter 8 in the textbook. And you can notice that after we use Legendre differentiation transformation, you can just swap the parameters in the function. And because of you swap to the function may have different meaning. So this is exactly what we talk about. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, internal energy, enthalpy, Helmholtz functions, and Gibbs function. Okay, so typically, Gibbs-free energy function G is kind of very suitable for us, because in an experiment, it is easier for us to control temperature and pressure altogether. But if you want to control entropy, wow, it's a little bit difficult, right? And you need to control volume to make it 100% fixed. This is still difficult, right? So Gibbs-free function is kind of more familiar with us. We are experimentist, right? So G is most important for us. Okay, and this is a table that really important. And then we introduce a memory squares to help you to understand or memorize it. And then we ask ourselves what is delta F, delta G means. And then we using this example to help us to know that the system wants to make the Helmholtz function go to the minimize as possible as they can. So when they reach the F minima, which means that the system is at stable equivalent states. So that's actually what this page tells us. Okay, and Gibbs-free energy also similar to Helmholtz function, but there's an extension we can add it here, because in experiments we are not typically only has the we are not only dealing with ideal gas, right? Maybe we can dealing with more complicated systems. For example, later we'll give you an example which is related to my PhD thesis. Okay, so you can see that actually you can you may have a non-mechanical forces. Non-mechanical forces maybe it's related to electric, maybe related to magnetic. Okay, so all these value is go to the WMM. MM means non-mechanics. So if this is a pure ideal gas, there's no non-mechanical force. The W will be 0. Okay, and then of course the G was still going to minimize and to make the system stable. But if you have a further mechanical things, non-mechanical things like electric applied on the materials, and then the thermodynamics theory still works. Okay, so this is how I show you the example. It's not important for your thesis. Okay, your research. This is my research. I just give you an example, demonstrate how classical thermodynamics helps me to obtain my PhD degree. All right, so let's come back. So, okay, I have done that. So I will start from here. Okay. Okay, so this is the application of the give function for my PhD degree. My PhD degree is related to the ferroelectric phase transformation. Okay, so for example, electric field applied to ferroelectric material. Ferroelectric material may has their polarization and switch its direction with the electric field. Electric field go up, the polarization go up. Electric field go down, the polarization go down. And this polarization can alter the shape of the ferroelectric material. So it can kind of, if you add the electric field, it will become elongated by the electric field. So it's quite, you can do a lot of accurate elongation by using these materials. So, well, let's continue. So, why the material may change their shape because of electric field? Because their tiny microstructure inside, just like this. Okay. For example, all these zones, the regions may have different direction of polarization. So, for example, if you have electric field apply up, and then these obviously maybe the total polarization is kind of up. So these two and maybe this is some sort of go down, go down. All right. So if these regions go down, it's not favorable for this one. They need to be cancelled by the electric field because the polarization is not electric field wants, right? So the way they do is that the material do is that the boundary, which called domain wall, will try to move forward. Will try to move forward to eat up, to consume the unfavored region. Okay, so you can see that these interface go try to make this region bigger and this region smaller and ends up nothing unfavorable. Okay, so then it will reach the equilibrium state. Equilibrium state. Okay, and this is E. So this is equilibrium state. Okay, this figure after we apply electric field. Okay, so the electric field obviously is this one. Electric field, right? And this is polarization. Polarization. Okay? So you can rewrite this Q equal to delta U plus P dV minus E dP. Okay, this P is not a pressure. It's a polarization, all right? So this is WMM, non-mechanical work due to the electric field you apply to the materials. And then you can see the minus delta G TP need to be less or equal to E D polarization. Okay, of course, this is minus WNM. Okay, so what we explained in the previous page is exactly looks like this when the theory applied to ferroelectric materials. Okay, and now this one is not really important. I just let you know that something in my thesis. Yes. So where should this non-mechanical for work goes to spend? The spending is moving this interface, right? Just changing the microstructure. So this work is go for moving this interface. So how to measure the interface? Easy. Interface just like a mass object. To move it, you move it, you can have half mv squared, something like that. But this m is not mass. It's the area, how difficult of this area be moved. So this is kind of mobility. It's a kind of a property of that area. And of course, the area, if the area become bigger, you need to you need more force, more works to do that. So basically, this is just sum them out all the interface energy of this to move that. Okay, so then after I using computer to calculate all this, and then we can successfully tracking the interface. So we can generate the hysteresis loop of ferroelectric material. So I graduated. That's it. So I really appreciate the classical thermodynamics helped me to obtain my PhD degree. I hope the classic thermodynamics can also help you to do that. So you can see that after I track all the interface, I can generate the material structure, the response of the material. It's really similar to experiment results. And so which means that we can obtain more detailed information in the microstructure. So that's how I graduate. All right. So that's it. Yeah. 中文就是说啊，上次不是讲到，就是如果今天 give free energy 是在 ideal gas 下做的话，那就正常，就是 delta G， 然后小于0这样子，然后它就让 G 跑到一个最低点就好了，然后就结束了。没有 delta G 嘛，就等于0了，就结束了，它就会 stable。但是如果今天有别的 non-mechanical 不是机械力的力量运用在这个系统里面的话，怎么办呢？那个系统它就会跑到，不好意思啊，就是跑到这边来啊，跑到这边来。那我就跟大家介绍一下 这个是什么意思？那在我正好我的 PhD 的论文就是做这件事情的。我在做铁电材料，我铁电材料呢，它的每一个区域叫做 domain，domain 有不同的 polarization 极化的方向，然后极化方向会被外在的电场所影响。如果外在电场是往上，它就全部都会想要往上。那像这个例子就是说，如果我往上的话，那很明显的就是它就比较喜欢这一种的极化量，它就不喜欢这一种的极化量，所以呢，他们就要把它吃掉。那怎么吃呢？它会用墙壁 interface domain wall 就是 interface 界面，会把它这样嘟把它吃掉。你看它就是用界面移动的方式把它吃掉了。那界面移动，你要推动这个界面，一定需要有一个能量嘛，对不对？哈，那这个能量其实就是我们刚刚讲到的 electric field 所做的功，负1底 P， 这个 P 是 polarization 的哈，不是 pressure， 不是这个 pressure，OK？然后呢，这个写下去以后，我们就等于是有一个力量在那里了。那要怎么样把它用掉？我们就假设它全部用在推动这个界面的能量上。那推动界面的能量怎么去算出来呢？其实跟我们平常在推一般的物件是一样的道理，物体是一样的道理，1/2 mv 平方，只是这个 m 原本是质量，现在变成原本就是这个 interface 有多难被推动，有多难被推动，那这样也是一个材料性质嘛，就跟你的 mass 也是一个材料性质是一样的道理。所以我们去量测出来它的这一个 interface 多难移动，然后它的速度会是多大，然后它的面积有多大？当然，越小的面积就越好推，越大的面积就越难推。所以呢，总体加总起来，它的能量就会等于这个能量 non-mechanical 能量。所以我就把它全部写成式写下来以后，就可以得到刚刚这个动来动去的微结构的式子。这些都是我用MATLAB 去写出来的。然后经过它的移动，然后它的整体的能量平均起来就会跟我直接实验量测出来的能量，迟滞曲线还要像，就是跟非常的类似啊，哈。那所以就是这样表示说我们的内部的微结构真的是这样子而改变的，那我们就可以从中获得一些资讯，然后我就毕业了，这样 OK。那我希望大家可以也能从这门课的 Classical Thermodynamics 或 Statistical Thermodynamics 这些热力学能帮助你得到你的学位啊，就跟他帮助我一样。Okay, next, energy. As well, kinetic energy, potential energy, internal energy is really easy. Okay, I believe you learned this in your senior high school, right? Kinetic means that the motion. The potential energy is that just like a spring or with the field, gravity field. If you put a higher, you store more energy, potential energy. Okay, internal energy is well, there's a condition. It's how you exist in this world. Okay, that's it. Energy, easy. Now let's talk about chemical potential. Chemical potential is that we are going from a closed system to open system because we are going to exchange the mass. So mass could be reduced, okay, or added up in the system. So we are now going to discuss the change of a mass with its own internal energy. You can imagine that everything has its own energy. Me and you are all energy in this universe. Okay, kind of physics, philosophies, perspective. But we are all energy. So basically, we have our own internal energy. When you add in the mass, the molecular or substance in the system, we're adding internal energy. Okay, so definitely we're adding things, internal energy will change. Okay, the added energy can be written as mu 底 n, mu 底 n. The mu is chemical potential. Okay, and then later we'll define this. What is chemical potential? Okay, and next, we can imagine that when we placing two particles, okay, when R become infinity, K equal to 0, V equal to 0, E equal to 0. So you can imagine that there are two particles, okay, and the distance between them is R, okay. So when the R is infinity, actually you didn't put into the same system, right? They didn't see each other, so everything's no interaction at all. Okay. However, if you bring out closer, bring up closer and closer and closer, and then you will follow the potential energy V here. You can plot that. Previously, there's nothing, no interaction. But once you closer enough, there will be a potential energy taking effect. And as long as it taking its own effect, you can imagine that the R, when R equal to R no, there will be a potential well here. When R equal to R no, here is the highest potential here. Okay, the highest potential here. So it shouldn't be highest. It's most stable. Okay, most stable, because it's the lowest potential. It would tend to stay there. But which means that at that stage, they store some energy in it. A minus V R no. K equal to V R no. So which means that if you want to take out of that particle at such stable state, at least you need to input the kinetic energy at such value to overcome this energy well to make it far away again. Okay, so you can imagine that this depth is actually how stable it is. Yeah, that's it. 好，我们要讲 chemical potential。我们要开始讲的原因是因为我们的系统不再是关闭的，可能是开放的，它可能会交换它的质量。那加入那个质量的话，它就会有能量加入进去。毕竟每一个东西都有自己的 internal energy， 所以我们就加进去的话，我们的内能一定会改变。好，那我们要怎么样想象这件事情呢？就是就原本如果 particle 很远，然后它根本就没有任何的交互作用，所以这个式就都是0。但是当它开始接近了以后，它开始有互相影响了，那这个式就可以开始写下来了哈。那我们如果它在这里的时候，它是最稳定的，它是最低的位能，那这代表什么意思呢？它就会很安逸的在那里。那如果你今天要把它拿走，那就要把这个 particle 推超过这个能量，那这个能量至少是要这个能量井的深度啊。 所以就是说，如果你今天把一个东西加进去了，然后它要，也就是说它已经在那边 stable 的话，它的能量状态已经改变，你要把它你要让这个能量改变，能量状态改变，你必须要多花一个这个东西，这个能量去把它抓出来。所以这就是一个你把东西加进去以后，对这个能量，这个系统的能量的改变。OK， so let's take more look, deeper look for the chemical potential. Example, with the acid with water, adding the water into the acid, we will increase the temperature. Okay, kilomole, okay, and the CP and CP water, CP acid, and close to zero. And yeah, that's it. And mass water is much greater than mass acid. So when we add in the water, heat gained by water equal to MCP delta T. Okay, so equal to here is a kilomole times the CP. Okay, delta T increase 0.1. So you can see that adding water, the heat gained by water is 418 joule. Okay, so for acid, mu equal to Q delta N equal to 418 divided by 10 to minus 5. So it's minus 4.18 times 10 to 7 joule kilo more minus 1. Okay, so see that because heat transform from acid to water. So mu is negative for acid. Okay, so the chemical potential per particle is that mu divided by 6.02 times 10 to 26 equal to minus 6.94 times 10 to minus 20 joule, or minus 0.43 electron volts. Okay, 1 electron volt is 1.69 times 10 to minus 19 joule. 1 electron volt. Okay, so basically just we adding the water in the acid. Of course, you're adding things. Energy will change and it will make the temperature increase, which means that heat gained by water and acid losing some energy. So Q heat gained by water, MCP delta T. So you can imagine that how this reaction to make the water gain the energy 418 joule, and because the acid transfer the heat to the water, so the mu, the changing of the energy of the heat is this one. Sorry, the chemical potential is this one because we need to divide its own delta M. Okay, and because the mu here is for kilomole, right? So if we want to know the per particle basis, we need to divide by the number of particles in kilomole, right? So each particle has chemical potential energy, this one. And because it is too small, minus 20. So typically we will use electron volt to measure the energy for each particle. Okay, 好，这只是一个很简单的快速的问题啊，例题啦哈，就是加了水以后，水从酸这边吸收了一些能量，然后它是增温了。那增温的话，因为这个增温我们可以量测出来，我们可以把它的焦耳吸收的能量算出来。那这个能量是从哪来呢？是从 acid 来的。那 acid 的话，它有10的负5次方的 kilomole， 那我们就可以知道每个 kilomole 它等同的chemical potential 是这么多。那这时候我们可以算它的一颗 acid 的分子会是多少。那我们就直接除以它1000 kilo， 就是一 kilomole 里面有几颗分子嘛哈。那我们就6.02乘10的26次方，然后除下去以后就哇好小的数字。那好小的数字，通常我们会使用 electron volt 去描述这么小的能量的单位，这样子。Okay, so previously we talked about one type particles. So this is page 8, right? Page 8, du TdS minus PdV plus mu dN. Okay, the mu dN is we only talk about one type of particles, one type of added particle. So if u equal to the function of SVN in the open system, you can separate them. The contribution of changing u can be ds, dv, dn, and of course the coefficient are all slope. The slope is actually this is t, this is p, and this is mu. So mu is actually related to the internal energy change per kilomole. Okay, so this is what we learned in the previous few pages. Then if we have m types, okay, sorry, grammar, okay, m types of particles are added to the system. We have many types. What actually we do is we sum them up together. All right, we sum them up together. If we have n types, mu j, the nj, the j is the type 1, type 2, type 3, type 4. Okay, and the mu j has more specific definition for this. Partial u over partial mj. Okay, and s v n k. So this is slope. This is slope like this. However, here SVNK, the NK is not only one types of particle. It is actually the rest of the particle. The rest is a multiple, more than one. Okay, so K here is not just one number. It's maybe, so if you are talking about mu2, the NK may be M1, M3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. Okay, so apart from the J here, okay, the rest of it. So yeah, actually the figures here is that we are going to adding NJ constituent into the system, adding, and here mu j is that everything else K, okay, are fixed. Okay, you can see that there's nothing here, right? No, we're just adding one type. Okay, that's what this page try to tell us. 好，那讲的是，如果今天是我们以 particle 一颗一颗来看的话，我们加一颗一颗 新的东西加到一个系统的话，我们只有一个新 particle 加进去的话，其实这式就很简单，写成这样。第8页就解释过了。那第8页解释过的话，这个东西前面的，就是我们的 U 啊，是 internal energy 会增加或减少啊，它的改变量有3个贡献。第一个贡献是 entropy 体积跟质量的改变。那当然这些参数系数就是它的斜率。那个斜率当然是要表示说，另外2项不变的状态下，另外2项不变的状态下，另外2项不变的状态下，好，这是一种 type。那如果你有多种 type 怎么办呢 ？n types 有这么多，没关系，你就等于是有很多个这个项，你就把它全部加总起来就对了。可是呢，有一个小地方要记得注意一下，就是一样，我们刚刚讲到的这些斜率都是在别人没有在变的状态下，所以你现在有很多个 n。你这个就不是只有3个哦 ，SVNK 这个 NK 的 K 其实不止一个数字，是除了 J 这个数字以外的所有数字都算作 K，OK？所以就是说，你看我要加这个 J 的东西，那其他的东西我们都不能变哦，所以这就是我们的 K，OK？好，大概是这样子。Right, so let's continue. Okay, so we can imagine that the U can be the function of S, V, N1, N2, N3, N4 until Nm. Okay? So how can we deal with this? This is a little bit tricky. Can we obtain more information here by using mathematic techniques? We observe that these things is actually extensive property. Everything here is extensive property. Extensive properties. You see that? S, V, N1, N2, N3, Nm, they are all related to mass, right? So extensive properties, they are all extensive property. So which means that they are proportional to the mass. Proportional to the mass. So this gives us a chance to play with it. We times a lambda. We times lambda. And which means that everything is proportional to the mass. So if we increase the mass by lambda times, so everything becomes lambda with a lambda inside, right? Lambda, m, m. So everything becomes lambda. And we say this is equation 1. Equation 1 can be seen as a homogeneous function. They are quite homogeneous because if you increase them, everything increases them with the same times, right? So this allows us to play a trick. If we differentiate differentiate equation 1 by lambda, then set lambda equal to 1. This is a trick, okay? Things become really interesting. U equal to partial U, partial lambda S, partial lambda S, partial lambda plus partial U over U partial V, lambda V, partial lambda V, partial lambda, okay? And blah, 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 blah. partial u partial lambda mm. Oh, almost break time lambda mm partial lambda. Okay, so I should give you a 20 minutes break, and then during the break you can set lambda equal to 1 to see what happened. All right, so I will see you after 20 minutes, and if you have any question, just come here. Thank you. All right. 最后一个实验，然后就不是。我说他是这个。isothermal process。好。这个，我不会。不要这个，因为这个是。对。好，看一下哦，你这个，是什么片的？哦，会不会是你只要转换一下就好了？因为 RT 跟 P，RT 跟P 是不是可以把它转换成一样？G 那就弄 PA，PV 等于 MRT 的话，应该可以哦，因为 PA 等于就是 PV 等于 MRT 嘛，所以 MRT 除以 V，所以它可能会倒过来，AB 倒过来，就倒过来，对啊，倒过来21，对，它倒过来，因为 NRT 都会被消掉。哎。
哎，因为那个就是练习第十页，这个
又到第16章，对，因为后面就教不完了，
因为考试的那个范围，
就是一整个学期，就是一整个学期的。
哦，那我可以问一下，
我们这一次的吗？
对对，这次的，
这次的应该是第10章吧，就是 PDF3，就是 Review 3它对应的章节，
是到第16
应该是你去看那个下一个是 Kinetic 啊，Kinetic 应该是我不知道是第11章还是第12章，反正那之前这样你就听得懂啊。
哦，
哎，应该 announce 会出来了，就是说
这考试的话就可以在一个
A4的，对对，你要看 announcement，应该是单面吧，对。 Okay, welcome back. Okay, so let's continue. Right. So I just talked about how we find the internal energy is actually is a function of everything about extensive properties. Okay, they are all proportional to mass. So which means that if I just adding times a factor lambda, and every factor also proportional to that lambda, we can imagine that the lambda is actually the increase of the mass, right? With the same times, the same scaling. So lambda to everything, all the parameters, it called homogeneous function because you see everything. If you increase one of them, it just everything increased at the same times, the same scaling. So we differentiate this equation by lambda itself, and then we do the trick to set the lambda equal to 1. What will happen? So after the differentiation, this one become S because lambda S to the partial lambda S over partial lambda S become S, right? Then this is V, of course, and this is N dot MM. No problem. But after we set lambda equal to 1, it become 1, right? It become 1. 1. Okay? And you can notice that this is actually lambda u over partial u over partial s, partial u over partial s, partial u over partial v, partial u over partial v, partial u over partial mm, and a lot of the rest of them, something like this. So you end up getting that, sorry, T minus P is a mu J. Okay, so everything become really elegant as T minus PV plus M J equal to 1 mu J and J. Okay, so from this point, we can have two routes. The first route, the first path is that if we compare with G equal to U minus ST plus PV, we can conclude that the G is actually J equal to 1 and mu J and J. So if we compare these two things, okay, we can obtain the first equation 1, and the second after we do the differentiation for this, TDS SDT minus PV minus PDV VDP, and this is differentiation, the front, the beginning, and differentiate the end. Okay, so we can have two conclusions from this. And then we will continue to compare these two equations in the next page. Right? 好，我们要讲的就是现在我们讲到 particle 有很多 particle 要加进去了，很多种 particle，n 种 particle 要加进去了。那这时候我们的 u 就可以写成一个函式，是什么呢 ？SV 的函式跟 n1 到 nm 的函式。OK， 那我们发现这里面全部都是 extensive property， 是什么呢？正比于它的质量啊，所以它们全部都是正比于它的质量。那我们就可以玩一个轨迹啊，就是说我们把它乘上 lambda， 全部都乘上 lambda， 因为大家都跟质量就是正相关嘛，那都是同样的倍率的，那我们就乘上 lambda， 全部都一起，你们就会发现这个数，这个函数我们可以叫做 homogeneous 的函数，因为它乘上一个 lambda 倍，那全部都乘 lambda 倍啊。那我们这边就可以做一个轨迹，就是说我们去偏微分 lambda， 然后我们再把 lambda 设为1，看会怎么样。因为这都是合理的事情嘛，对不对？好，我们就对它做合理的事情，但是是一个轨迹。我们做完这个事情以后，发现哦，这个式子是 s， 这是 v， 这是 mm， 没有问题。那再设定成1以后，那 partial u over partial s， 哎，那不就是 t 吗？那这个不就是负 p 吗？啊，这不就是 mu j 吗？好，所以说把这个上面的式子写成这样子。那这个式子写完以后，再把它简化，这个斜率正好就是 s， 不好意思 t 负 p 跟 mu j。那写完这个以后呢，我们就可以跟这个式子来比较，我们就会发现 G 就会等于这个东西，这是第一个我们的结论。第二个结论就是直接把这个东西做微分，改变量啊，前微后微，前微后微，前微后微，然后就变成这个式子。所以有两个式子，我们等一下下一页会继续的比较。Okay, so let's continue to compare these two equations to get the well-known Gibbs-Duran equation. Okay, we compare two equations and then we found that SD T minus VDP plus sigma M J equal to 1 MJ D mu J equal to 0. So this is the famous Gibbs-Duran equation. And it is really useful for us experimentalists. Okay, if temperature and pressure set to constant, right? This is always what we do for our experiment, right? Then everything becomes simpler. Sigma n j equal to 1 and j d mu j equal to 0. Okay, and then if we focus on G, the change of G become this one, right? Because this is differentiate the beginning and then plus the differentiation for the back, the end. And then we notice that this one and that one become 0. Of course, if at the condition of constant Nien-Ti. So during our normal experiment situation, the G T equal to sigma M J equal to 1 mu J D N J. Okay. So Gibbs-Duran equation really suitable for us for our experiment. So this is why it's so important. TP and constant. So the change of G is purely the change of n times its own chemical potential。好，我们要解释如何得到有名的 Gibbs-Duran equation，不用翻译了哈，也没什么意义嘛，好，然后呢，接下来我们就我们就比较一下前面前面一页得到的两个式子，我们就会得到这个东西。那这东西呢，我们就会发现一件事情，底 T 如果是维持为0的话，也就是我们在 Tp 为定温定压下，那就是我们平常在做实验的状况。好，我们常常都会这样设定嘛，不然也蛮难设定的哈。好，那这样设定完以后，我们就会发现这些都为0了，就变成这样子，也等于0。好，那这等于0的话，我们去比较一下 G。这个 G 如果我们看它 G 的改变量，改变量会有2个贡献，前后的贡献。好，那前后的贡献呢，如果在 PT 等于0的，就不是等于0，不变的状态下，这一式就会等于0。好，那这是等于0的话，也就是说我们的纯粹的在通常的实验状况下，我们 G 的改变量就会是纯粹 μJ 乘上 NJ 的变化量，然后加起来。Okay. So now, next one, let's talk about phase equilibrium. When we have a self-contained system with phase A and phase B, and it at its own equilibrium, which means that they are stable, right? Phase A and phase B stable. We should know that the stable in our real world is actually not really fully rest. They actually get a balance between the exchange, right? So this is not really a stable, not really fully rest condition. It's kind of exchange at the balance. Okay, so phase A turning to phase B, and phase B turning to the phase A at the same time, and with the equal volume, equal everything. Okay, so it's called phase equilibrium. So in this container, no heat flow, no work down, just there, everything's stable, but underneath they has their own exchange, but with equal sign. So you can conclude that change of NB and change of NA are the same value, but with different sign, right? And the volume, of course, the change of the VB is also equal to change of VA with with opposite sign. The internal energy is also DUB, DUA again. So these three are famous. Conservation of mass, volume, and energy. They are all, common sense, right? Then we can introduce one more things. This can be acceptable, right? DSB minus DSA is fully equilibrium. So change of S equal to DSA plus DSB equal to 0. Okay, so you can accept that, right? Accept that here. Okay, minus sign. So if we put them together, dUA equals TA dSA minus PA dVA plus mu A dNA, and we have exactly the same set for phase B. What we are going to do is that we do the plus. Okay, if we do the plus, anyway, if we sum it all together, oh, by the way, this value is come from page 18. All right, these equations come from page 18. So if you don't understand this, go back to 18, 3 pages ahead. Okay, and then after that, we can sum it all together, become the equation like this, longer equal to 0, right? And then interesting happened. you can notice that the A, the UA, the VA, the MA is actually can be any values, right? They can be any value. Change of the U, change of V, change of N can be any value. When they do the any value, which means that, and they also need to always satisfy this equation with the 0 in the right-hand side and the right-hand side, which means that there are only one condition can make it happen all the time, equal to 0. Their coefficient equal to 0. Right? So, conclusion, at phase equilibrium, temperature AB need to be equal to 0, equal to each other. EA, PB equal to each other, mu M, mu B equal to each other. So which means that thermal, no problem. Mechanical, no problem. This diffusive, which means that their particle diffusion, they will have equal chemical potential. So you can imagine that chemical potential is kind of the potential that pushing the mass to the other end. When they have equal chemical potential, which means that they are the same. They don't need to exchange their they don't need to push the boundary. If you have higher potential for phase B, which means that the phase B, the interface will move to achieve the equilibrium. Okay, but now here they are equal to each other, so the boundary won't change because the diffusion of the atoms maintaining a balance in this system. OK， 好，我们今天要讲的是相平衡。我们有一个系统，那个系统它没有热流，也没有外语的多余的功，它就是在那边很正常在那里，很平稳在那里。但是所谓的很平稳，不是全部都休息哦，它其实是有在秘密的交换，只是交换的值都是一样的，所以我们会看不出来啊。那所以什么意思呢？就是它 conservation of mass， 就是它的体积的交换、质量的交换其实相等的，但是正负相反，正负号相反的，那 V 也是 U 也是 S 也是，所以我们再根据第18页的式子呢，写出这两边 face A、face B 的东西，把它加总起来，我们就会发现它们要等于0。好，它们要等于0以后呢 ，DUA、DVA、DNA 其实是一个改变量，它其实可以是任何一个值的，只有在一种条件下可以。在这些都是任意值，但是却又等于0的状况下呢，怎么办呢？只有这一种状况，就是它们的系数都为0才会是可能的。所以说，这代表一件事情 ：phase equilibrium 相平衡的状态下呢，你一定要在温度也是平衡的状态，两个相的温度要平衡，两个压力要平衡，而且它的 chemical potential 要平衡。那这个 chemical potential 其实它的意思就是说，他们不会由一方多流到另外一方比较多。好，那如果比较多的话，表示说它不平衡嘛，对不对？好，所以它 diffusing 它就是会有扩散的之间的平衡。Okay, now let's step backward a little bit. Okay, step backward. Okay, if we are examining before the equilibrium state is reached, before just tiny step. After this step, we reach equilibrium. Okay, so which means that the system is during the process that delta S equal to delta S A plus delta SB greater than 0. So which means that it's still evolving, So let's examine a little bit. So if the phase A and the phase B just need one more step, one tiny delta NA exchange to delta B. Sorry, it should be mass flow. We should say mass flow. The NA need to flow from A to B. So before, so this is equilibrium state we mentioned in the previous page. But before that, just one step. Once the delta NA switch to NB, and then they reach the equilibrium state. Okay, so if we just make the hypothesis, okay, if just delta NA transfer to B and then everything done. So which means that the delta SA, delta SB is purely, and the rest of them, UA, UB, they are all rich. They are all reach their equilibrium state. They are okay. All right. So of course, the UA equal to 0, the VA equal to 0, and the UB equal to 0, the VB equal to 0. So which means that delta SA are purely equal to the mass flow. Okay. Then if we do that, we can summon that together. We can get delta MA divided by T mu A minus mu B is greater than 0. Okay, so here, summon that together. Right? And it tells us, oh, mu A is greater than mu B. So which means that if mu A greater than mu B, the mass flow must flow from A to B. So which means that mass is higher chemical potential to lower chemical potential. And you can use exactly the same trick to see heat and volume for this. All right. So heat, hot to cooler. Volume, high pressure to low pressure. Right. It's straightforward. Mass, we just show you mass is higher chemical potential diffuse to low chemical potential. OK， 好，我们现在解释了，刚我们介绍完等效相稳定的状态，那我们现在来更难一点点，就是往前推一小步，一小步，它还没有 equilibrium， 它还没有稳定，它还只有一点点，它还差一步，什么步呢？我们只差我们的 mass 从 A 流到 B， 让它从 NA 加 delta NA 变成 NA， 它少了这个 delta NA， 然后这个 NA 去哪里呢？去 NB 去了 ，OK， 去 B 呢 face B 去了。光是这样做一件事情，好，它就达到 equilibrium 了，它就达到稳定状态了。那这样会怎么样？它会有什么样的现象呢？我们就来用数学来看一下。当然了，我们假设 UA、DA、VA、DV、DVB 都已经是完全稳定了，就只差这么一小步而已哦，就只差这么一小步。好，那所以 delta SA、delta SB 可以写成这样的式子，然后呢，我们再把它加起来，一定会大于0嘛，哈 ，delta SA、delta S 大于0。好，写出来以后，我们就会发现，哦，原来 mu A 大于 mu B， 也就是说哈，我们假设我们的这边 A 要流到 B 去的话，会有一个现象，它就一定会，这就是带给我们一个条件，就是 mu A 大于 mu B， 那这样它的 NA 才会流向 B 去。OK， 好，那大概就是这样。Right, next one we talk about more, well, interesting. Give phase rule. The give phase rule is actually related to phase diagram or phase diagram. So when we do the experiment, we can choose certain conditions for the experiment, right? For example, if we choose certain temperature, if we choose certain pressure, if we choose certain certain molar fraction, the composition we mix up, right? We can define that. So you can imagine that the T, P, and molar fraction is actually what we determined. We can choose by human, right? So if we talk about an experiment we are doing, we want to generate some chemical stuff. We're going to do that. We can choose the temperature and pressure. So the temperature pressure is fixed by human. Okay. So here, two independent variables. Okay. We also call this degree of freedom. Okay, so which means that this is selected by human. We can choose it freely. So this is a degree of freedom for us, for human. All right. So now we assume that we fix the temperature and pressure, and then we are going to create the new stuff, the new chemical component, chemical compound. Okay, so assume that chemical compound has k constituents, k things in it, and each of them has pi phase system. So pi phases, for example, gas, solid, liquid, three types of system. Sorry, three phases. Okay. So in this case, pi equal to 3. Okay. So for example, you have several constituent, maybe CO2, O2, mix them together, and they may have three types of phase. Okay, something like that. Okay, so here we're going to give you a more general mathematical configuration. So you can have k constituent pi phases exist. Okay, so now because you are going to reach a equilibrium state, because you need to make things up. So you make things there, they must be equilibrium, otherwise it will become other things, right? So equilibrium is all we need. We just talked about equilibrium. It's all about mu equal to another mu, so they won't diffuse each other. So which means that mu I1, mu I2, mu I pi, they all need to be equal to each other. So this is one equation. This is two equations. So this is equation 1, equation 2, and this is equation pi minus 1. Minus 1, because 1 to pi, the equal sign will less than 1. I mean, minus 1, then pi. So here you have pi equation for each constituent, and then you have k, so you have k times pi minus 1 equation to satisfy. Because this equation need to be satisfied for us, for human, this is a constraint. Okay, this is a constraint. We cannot alter it. We cannot change it. Okay, so I use yellow line, yellow highlight. Again, next one, what we are going to consider is the molar fraction. Molar fraction, molar fraction, you can add out by yourself, right? So you can choose K constituent and you can choose K pi. So they are all independent variable. Okay, so this is degree of freedom 2. Degree of freedom. Another constraint here is that all the molecular you set ends up, you need to sum it out as 1. All the fraction you set need to be summed out as 1. So there will be pi equation because there are pi faces. So now sum them out together. Pi plus k times pi minus 1, 2 plus k pi is the degree of freedom. So the number of degree of freedom left will be f equal to k minus pi plus 2. So when you talk about the phase diagram, this is kind of important for that. Phase diagram can be a 2-dimensional, 1-dimensional, 0-dimensional graphs. So based on this one, we'll give you a quick example, really simple example in the next page. But now I need to have a translation here. 我们要告诉大家介绍 give phase 的规则项规则。好，我们假设我们要去做一个东西做出来，那个东西其实在做实验的时候，我们可以选择它的温度跟压力，我们也可以选择我们要 mix 的浓度是多少。那所以说这些人可以选择的，我们叫它自由度哦，自由度 independent variable 自由的 ，OK 我们自由选择。但是呢，为了要做出一个稳定的东西，它们之间的 chemical potential 一定要相等，不然的话它们就会动来动去 diffuse 动来动去嘛，所以它是不等。所以为了要做出稳定的东西的话，还是需要有一些束缚条件要去满足的。接下来我们就要讨论这个束缚条件。那我们假设我们有这个系统里面会有k 种不同的东西，不同的物质。那有几种 phase 呢？要考虑呢？有拍种 phase。那当然最简单的就是固体、液体、气体3种。当然还有如果有其他种更复杂的项，那当然是可以继续考虑进去。那总之呢，我们有 k 种的话，有拍种 phase， 那就会需要去满足这么多式子，这式子是每一个 pi 的 phase 都要相等啊，它的 chemical potential 都要相等。所以呢 ，equation 1、equation 2，每一个 pi 1到 pi 的所有之间都要相等，那这样就会有 pi 减1个式子要满足。那 molar fraction 是我们自己考虑的，我们爱给几个 percent 就给几个 percent， 所以 k pi 对我们讲是 degree of freedom。但是我们自己加这样子乱弄的话，后来总是还要有一个条件，就是他们加起来是100%，所以这不可能不符合嘛，哈。所以说这边又是我们的束缚条件，有拍一个。那接下来我们把它全部加总起来，相减以后，我们就可以就是自由度减掉不自由的 constraint 的束缚条件。那这样我们的 degree of freedom 就会变成 k 减派加2。那 k 减派加2表示说这自由度剩下的自由度表示说我们接下来是可以去人类就可以 tune 去决定的，那就是我们的 phase diagram。phase diagram 对我们来讲就是地图一样哦，下一页就可以讲到了。So we give a really simple and quick example to explain Gibbs phase rule. So F equal to K minus pi plus 2. So here we only can consider one, for example, carbon dioxide. Okay, K equal to 1. So F equal to 3 minus pi. So we can see that the degree of freedom, how many degree of freedom we can have. You can see that in triple junction, triple point here. The triple point here is the phases coexist all together. 3 points. three phases. Three phases coexist together, which means that pi equal to 3. 3 minus 3 equal to 0. So the degree of freedom will be 0. So 0 degree of freedom, 0D. 0D is a point. You can see that there's nothing, no freedom left, no degree of freedom left. So we only can find one point for coexist, three phases coexist conditions. And then you can see that if we have liquid and gas coexist line here, we can say, we can say this is two phase, sorry. So two phases coexist. So it is 1D, 1 degree of freedom left. So it's a line. It's a line. Okay. And if you only have one phases, you can have two-dimensional degree of freedom. So it can kind of plan for you, area for you. Okay, easy. 好，马上试用，就是运用一个最简单的例子。假设我们的 K 只有一个，就是只有二氧化碳。二氧化碳的话呢 ，F 就等于3减派，这派就是它的相的共存的个数。你看哦，你的相共存的个数，如果今天是固、液、气全部都在一起的话，这边就是3，3减3等于0，也就是说它是0D 的，没有任何的 degree of freedom，它就只存在一个点。但是呢，两个 phase 的话，3减2等于1，它就会有一维的自由度，它就变成一个 line。那如果今天是只有一个 phase 的话，就会有两个 plan，两 2D 就是一个 area。OK， 那就大概是这样子。Next one. Let me draw a line first to divide this page into two. Okay, actually I mix two concepts in one page. So sorry for that, but we just introduced the first one and then the second one. Okay, mixed process for ideal gas for pressure. Okay, for pressure, mixing process for pressure. Let's take a look. So if we mix two ideal gas, two ideal gases are easy, right? So because ideal gas, the assumption of ideal gas is that they actually cannot see each other. Okay, they don't have any interaction. The volume, atom volume are really small. So actually they don't see each other. They kind of penetrate them together. Okay, so you can imagine that the total pressure is actually the summation for each of them. So Pj, if we have two ideal gas, P1 plus P2 equal to the total P. That's it. So Pj summation Pj equal to summation Nj over M. So it's actually the total pressure times its own volume fraction. Okay. Not volume fraction, sorry. It's a mass fraction. Sorry, this is a mass fraction. X is a molar fraction of the J constituent gas. So each gases in this container has its own molar fraction, mass ratio. Okay, if you times mass ratio to the P, total P, you can get its own Pj. Okay, so that's Pj equal to Xj times P. This is what we learned in the ideal gas mixing process. Next one, mixing process for Gibbs function. What will it looks like? For Gibbs functions, Gj is similar to Pj. It's a specific Gibbs function for each J constituent. Okay, so maybe the second type's gas or the first type's gas in the container. So G equal to summation of Nj Gj, no problem. Okay, and then for in page 8, we know that G equal to H minus Ts, right? So H, remember H? In review 1, page 15, our ideal gas, the H equals H minus H naught equal to T naught T CP dt, right? In review 1, page 15, we know that H minus H naught equal to T0 T integration CP dt. If we can accept that, we just substitute here to here. So you can end up CPT plus H naught minus TS. Okay, okay. And of course, we can sort of tell you what does that mean. The H naught means the enthalpy, the enthalpy at 0K, at 0K. All right. Now, let's continue. How about TS? TS. TDS equation 2 can help us to get this one. TDS. TDS equal to CP dt minus V dP. We do the integration and we can get S equal to this one. And luckily, we can substitute this to S. And then we can obtain a RT natural log P plus, okay, constant. Okay, the constant is actually function of T. It include what? It include RT CPT. Hey, wait a minute. If I write it here, it's better. Okay. CPT minus CPT natural log T minus TS naught plus H naught. Okay. Don't worry, I can highlight it for you. Don't be afraid. Yes, yes. And then here, and here. All right. So the phi looks terrible, but actually they are all the temperatures function. Okay. So the phi t is actually this one. So because if you if you substitute into this and then become very much longer, it's ugly, right? We just make it shorter, become fine. Okay, and then we will use this later on. All right. So you can see that G is actually RT times natural log P when we and plus a constant. And the constant is a function of T. If you have fixed T, everything will be constant. And then the mixing process for ideal gas, the G behavior will look like this one. Okay, and we will use this later. All right. 好，我们开始讲啦。就接下来我们要看混合 ideal gas 会造成什么样的现象。首先，混合这边这一页我把它分成两部分了哈。第一部分是针对压力的状况下来看，它压力的话，其实 ideal gas 在压力的状况下，其实只要看的就是你有两个理想气体，其实它们两个是互相没有看到彼此的。你就想象它，因为它没有 interaction 嘛，它没有交互作用，然后它们的体积又假设非常小，没有，近乎没有，它们几乎是看不到彼此的，所以等于是两个叠加在一起那种感觉。那所以说它的 pressure 其实就是加总起来就好了。那我们加总起来就是纯总 total 的 P， 那它们之间正好就是它们的质量的比例乘上去以后，就可以得到个别的压力是多少。这是上面讲的 Pj 等于 xj，xj 就是它们的摩尔比例，摩尔比例其实是质量比例啦啊，有越多当然就是占越多的压力，就这样。好 ，xj 乘上总 total 的 P。好，那接下来呢要讲的就是 give function 了，在 mixing process 里面的 give function 长什么样子？好，我们的 G 一开始就长这样了哈，我们写第8页可以知道 G 等于 H 减 Ts。那 H 呢是在ideal gas 的时候呢，它会是 H 减 H no 等于 Cp 的积分，这个在review 第一的第15页里面我们讲过了，然后我们就把它拿过来用，结果呢我们就写出来以后得到这个式子，那 H0 我们提醒大家一下是 enthalpy 在0K 的时候的值，是一个常数。好，然后接下来呢，这个 Ts 要怎么办呢？我们就用我们之前在影片中讲到的 TdS equation 2。TdS equation 2呢，也是用 Cp， 然后做一个积分以后就可以得到 S， 然后长这样子的式子。代入 S 进去以后，会得到肉长的式子，非常的丑。那我们后来发现，其实这些绿色的跟黄色的，其实就是温度的函式，所以我们不如我们就把它写成 phi 吧 ，phi 就写的比较简单了。就如果今天温度定温的话，那这里完全就真的就是一个常数了哦。好，那所以说我们把这个 phi 写下去以后，就把它简化以后，我们的 G 就可以写 RT natural log P 加 phi 了。OK， 那这个东西就是在 mixing process 的时候，它的 G 的表示方式，我们接下来会使用到这个东西。OK，so next, after we talk about pressure and give function, then we are going to apply them into mixture of the ideal gas. Initial state is N1 TP, N2 TP, okay, and GI N1 G1, N2 G2. Okay, no problem. This is initial. And G1, of course, RT natural log P plus phi 1. RT natural log P plus phi 2. Okay, no problem. We just learned that before, right? No problem. Initial state. After mixing constant T, final F, N1 plus N2, P1 plus P2. GF, G final state, N1 G1F, N2 G2F. Okay, and it's very similar to what we done. RT natural log P1, RT natural log P2. All right, and then the P1 is X1P, P2 X2P. So you can see that everything we mentioned here is in the previous page, right? So the GF equal to blah, 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 blah. Okay, so the GF, if we compare with G here, so of course, in this case, all right, I guess I need to give you 10 minutes break. So I will continue this problem topic after 10 minutes. See you later. If you have any questions, just come here. Thank you.
When I my homework
Yes.
is in 6A.
Mm-hmm.
The DA said the PV equal to RT. So with the N.
The V, okay. M, if there's no M, which means that your V is actually a small letter.
Oh.
So small letter means that you divide by M, capital V, divide by M becomes small v. I guess this is the problem, right?
Oh, I see.
Yeah.
Actually, I confused about the V capital and V small. So if I use the all V capital, it's okay.
Yeah. But which means that you are talking about the system that if your calculation, I mean, if you use capital V, everything need to be capital V. Capital S, capital something, SC, capital C. So if you using small p, small v, so your C can be small v and small p and S small s. So you need to be consistent. If you divide by m, everything should be divided by m. Yeah. You need to be consistent.
I think I need to learn more.
Yeah. Just practice. Thank you.当然，
就是这个，这个怎么对？这个
牛肉相当。OK，这个你可以吗？这边可以吗？
可以。
所以如果这边的话，底 PV 属于底，对它做微分，就变成微分前面乘后面，微分前面乘后面，微分后面乘前面，这个就是这两个，应该没问题吧？
可是不是对体重会的。
对，所以它这边会有底题啊。这边好，那先这边有底题好了，这边有底题，除以底题，然后这边的 RT 的话，对它做微分，就会变成 R。
不是，意思。
然后这个底题移到右边去就好了。好，所以实际上这个东西就是底 P 底 T 乘上 V， 再加上底 V 底 T 乘上 P 等于 R， 然后把底 T 再移到右边去变这个是
高感风，就是这个数字。
OK，好，刚刚好像同学有来问过，就这第10页嘛，对不对？这第10页的时候，10页这里就是那个，这个是 PAPB，跟你的 B 不太一样，对不对？
对
对，但是 P 就等于 PV 等于 nRT，对不对？
嗯。
然后 P 跟 V 会等于 nRT 的话，nRT 就代表他们是反比数。对对对，所以说你看到那个是 VA 在下面 V，
哦，所以它是颠倒。
对，是颠倒的。所以你看一下，啊，的确是2跟1，它是相反，一个是原本是 P1 P2，现在变成 V2 V1 的。好，
哦，就是这两个为什么会相等？
哦，OK，好，你如果做这个，你这个这其实在那个什么，我基本有教。好，总之就是你做这个东西的积分，就会回到这个，刚好回到这个。你试试看，就是你如果从这边推过去很难，因为你就觉得怎么会这样？但是如果你从这边吸回去，就这个东西的确就是你这个灰色的，因为你看哦，dx 跟 dx 要做积分嘛，它不就就积回这边 n 啦，它就 n 嘛，然后呢 n，然后这边是带减 a 的、啊，这边是减 b 的，这边是 b 减 a 啊，所以 n 带 b 进去就是 nb 啊，这 a 带进去就是 na 啊，所以刚好就积分
那我
过去
就这样。
就回到这里来。OK，好，
谢谢。
谢谢。
Okay, welcome back. I think, yeah, we can finish that in time, right? And there's no way if we can finish in time if I don't provide video teaching. Otherwise, next week we cannot have our midterm on time. Right, video teaching is quite easy, quite nice. Really, I hope it actually similar to what I'm doing here right now. I don't know. How do you think? 我的意思是说啊，就是如果今天我没有用 video 上传的话，应该来不及了吧？绝对来不及。那我就觉得，video 很方便啊。那这时候就会想说，那大家在现场会真的比较有用吗？还是在家里看录影带比较有用呢？那如果是这样的话，我是以后都不用上课，只要上传就好了 ，OCW 就好了。所以我觉得有点奇怪，还是说只要 OCW 大家看完，然后来这边问问题就好了？对，搞不好这样子的方式会更简单。不过我不知道了哈，这都现在的教学有非常多的多元的状况，蛮好的，就是看大家可以自由挑选自己喜欢的方式这样。All right, so let's continue. So we just finished the previous page, right? We have discussed the mixing process for ideal gas, how to effect, how they affect the pressure and the gift function. Okay, and the gift function can be written in RT natural log P plus a constant. Okay, so initial looks like this. Final looks like that. And each of the N1, G1I, N2, G2I, N1, G1F, N2, G2F, they can written down into the formulation we just explained in the previous page, right? And P1 is P1. P1 equal to X1 P, P2 equal to X2 P. So we can write down like this long things. All right. And if we compare with the definition of G here, in this case, G F equal to N1 mu1 N2 mu2, no problem. So we can compare this. We find that N1, N1, N2, N2. So the rest of it are mu1 and mu2. So it tells us chemical potential is actually T natural log P plus phi plus natural log X. It also equal to G plus RT natural log S. Chemical potential looks really beautiful. 好，我们刚刚讲到混合嘛，混合初始条件的时候，它的 G initial 可以写成初始 G 可以写成 N1 G1I N2 G2I G1I G2I 可以写成这样子，这个没有问题，前一页也讲到了。那 final state 的 F 的话呢 ，GF 会是 N1 G1F N2 G2F，OK，、然后 G1F G2F 又可以写成这样子，也是前一页讲过了。那更甚就是 P1 P2 可以写成 X1 P X2 P， 然后把这个东西写的很长式子写出来以后，把这个东西带进去了哈，写成很长式子以后呢，我们就可以比较 G 的原始定义。那原始定义这边有 n 个嘛，现在只有两个气体啊哈，所以在这个 case 上面，这个 mu1 n1 加 mu2 n2 就长这样子啦。就我们发现这两个东西非常的像 n1 n1 n2 n2， 哎，那就表示说剩余的这个东西就会是我们的 mu 咯。我的 mu 就写下来，就写成这样子 ，mu 等于 g 加 rt natural log x。我们既然找到了 mu 长什么样子，好，那我们接下来继续应用哦，还没完 ，we haven't finished yet. We need to apply what we found. Okay, so again, Gi N1 G1I N2 G2I, which is initial state. GF N1 mu1 N2 mu2. Okay, so if we want to find the delta G, GF minus GI here. So this one minus this one. Okay, so again, we can mu1, mu2. Let me give you a hint that mu1 is actually G1I plus RT natural log S1, right? And mu2 can also do exactly the same stuff. So if we sum them up together, the only thing left is N1 natural log x1, then N2 natural log x2. Okay? So everything becomes even more simpler. MRT x natural log s1 plus x2 natural log x2. Okay? And x1 and x2 are always positive because this is a molar fraction, right? Either 0.5, 0.6, 0.4. So they are all positive and less than 1. So which means that the delta G will always less than 0. Fit the result. We fit our common sense, right? 好，我们前一页讲到就是刚刚讲到 mu 等于 G 加 RT natural log x， 对不对哈？还没有结束，我们要把它应用在这里喽。我们的 G 前面是这样写 ，initial 是这样写 ，final 是这样写。好，相减之后就会得到这样子的，相减之后会得到这样的式子。好啦，可是这个 mu1 mu2 啊哈，又可以用我们前一页写到的这个东西，那正好就可以把一些抵消掉啊，抵消掉删掉以后呢，就剩下这个了。那这个剩下这个呢，把 n 移出 n1 n2 移出来是 n 乘上 x1 n 乘上 x2， 这边是不是少写一个 1呢 ？OK x1 natural log x1。好，那这样算完以后呢，我们就会发现一件事情 ，x1 x2 是 0.4 0.5 0.6 0.7这种东西。它是比例嘛，哈，0到1之间的比例，所以说它一定是正的，小于1的，所以它的 natural log 一定会是小于0的，是负的，对不对哈？所以说两个加起来一定是负的，那当然我们的 delta G 就绝对是负的，这跟我们的 common sense 我们的常识是一样的，完全符合。OK, next one. So again, in the P8 reciprocity relationship tell us that S is actually equal to minus partial G over partial T, a constant B. So delta S equal to this one, of course. And delta G can be substituted by the previous page. Da-da-da. So after we done the differentiation, delta S equal to minus MR times this one. Again, X1 and X2 are 0. I mean, X1, X2 are in between 1 and 0, and this is a positive number. So which means that this one will always minus, and minus times minus become positive. So delta S always greater than 0 during the process. Everything fit our common sense. So how about the two gases with equal volume are the same? This is called Gibbs paradox. So N1 equal to N2 and X1 equal to X2, half. So after you've done that, the delta S actually greater than 0 for N are natural log 2. Yes, but if two gases are exactly the same, it should be after the mixing, they actually nothing changed. Even the entropy doesn't change. So this is called Gibbs paradox. Entropy change for the same gases should be 0 because they are the same. So the only difference is is the wall. Just take it off, and then everything will remain the same. So this problem is Gibbs paradox, which means that it cannot be this theory cannot explain this special case, but the problem can be solved by statistical thermodynamics, which means that later we will discuss this problem again by using statistical thermodynamics. Then delta S equal to 0 in this new theory, well, relatively new theory. Okay, we will discuss that later. Maybe next few chapters. 好，我们继续下去哈，就是刚刚前面那一页得到的结果啊，得到的结果，我们其实还可以再应用一次到我们使用第8页的相互的这种关系，找到 S 其实是会等于这个嘛哈。那 delta S 呢，一样也是可以把它写成这样，因为把 G 带进去了。算进去以后呢，我们就发现刚刚的 X1、X2 还在里面，那 X1、X2 是是0到1之间的数字，会让 natural log 变成负的。那负的又乘上负号，就会变成 delta S 永远都会是正。OK， 那跟我们的常识也是非常类似的。那接下来要讲的就是 Gibbs 的矛盾啊，也就是说，如果今天两个气体是当混合气体是两个不一样的气体，但如果是两个一样的气体，而且它们体积相同，那等于是说你做这件事情纯粹只是把中间的墙拿掉了，把中间墙拿掉，其实根本对他们来讲一点差异都没有，所以实际上真正的 delta S 会等于0。但是在 Gibbs 就是我们在算这个东西的时候，我们并没有考虑它到底是一样还是不一样，所以 Gibbs function 这边算出来的东西其实还是会大于0，那就表示说对于这种特殊的情况下，这个是有问题的，这个理论是有问题的。那 statistical thermodynamics 统计热力学就不会有这个问题，我们就可以跳过这个解决这个矛盾。好，那以后会讲到。Right, finally, the third law. The third law is that there exists a lower limit to the temperature that can be attained by matter, called the absolute zero of temperature, and the entropy of the all substance is the same as the temperature. Okay, so let's write down the S. So you can imagine that the S is actually, previously we all talked about the change of entropy, because we all care about the change. But when we do the integration, we always has one integrating constant called S naught. The S naught is actually the one additive constant, integrating constant at 0K. Okay, at 0K, S naught. And there is called a Nernst theorem. It is limitation t to 0, S1 minus S2 equal to 0. So everything's their difference S1, S2 when they come to the temperature really zero, really low until 0K, their difference should be 0. Okay. Another Planck's constant statement is that S equal to 0 when the temperature going to 0, and the proof will be shown, can be seen, can be found in page 172, 173 in textbook. And we are not going too deep to talk about that, but we could anyway. Right. So we're not going too deep to talk about the Planck statement, but we will show you one relatively difficult to understand the proof for Nernst theorem. Okay, Nernst theorem is kind of interesting to talk about. Okay, and we need to say that Nernst postulate is that unattainability principle, which means that actually we will never reach we will never reach the temperature 0K. Okay, this is really difficult, and we will never attain the 0K. So if we base on this rule, we can borrow this, we can have this help to prove Nernst theorem. Okay, and the next we will talk about that. 好，我要讲就是第三定律就是说有一个 lower limit 就是总会有一个下限哦，这个下限它是大家温度都到那里，然后都是0，然后它的 entropy 都会是0这样子。OK， 那也就是我们之前在做积分的时候常会出现的这个积分常数 S0 啊。那这个 S0呢，就是代表在然后 Planck statement 就会说这个 S0会等于0啊，哈，大概是这样。好，那这个 proof 会在这里，大家回去可以看一下。课本上还有另外一个证明，那个证明有点 tricky， 有点奇怪。那之前学长姐都会问我，那所以我就把它拿过来这边问，就是直接讲给大家听。那它是证明 Nernst theorem。这个 Nernst theorem 就是说，当温度变到0的时候呢，它的 两个状态 S1、S2 会差距会越来越小，越来越小，它们的之间的差距会越来越小。OK， 那因为差距越来越小，这个差距越来越小，要怎么证明呢？我们要讲一个就是 Nernst postulate， 就是说，其实我们是无法达到0K 的，因为那太难了，我们没有办法让温度下降到这么多啊，我没办法，这是没办法，因为它是一个 lower limit。lower limit 就是你永远找不到它的下界，对，你永远到达不了，就是你永远都无法到达那个地方去。那这件事情我们等下可以证明给大家看。好，那这就是等下可以证明 Nernst theorem。OK， now Nernst theorem we want to prove that the two states S2 and S1 at 0 k equal to 0, their difference will be 0. Okay, we want to prove that. So we know that this is the concept we need to tell you first. We know that absolutely zero temperature is unattainable. We never attain the zero because we say lower limit. You always find the lower limit, lower limit, lower limit. You cannot find that. You cannot reach that. And also, you know that S equal to S naught plus the ST0 integration d bar QR over T, no problem. And this is typically by using T capacity to do the integration divided by T, right? But here you see that why I didn't put T or V here, because it doesn't matter. It doesn't matter. Okay. You put T or V here, it doesn't change the result. So we just take out the P or V. You can put that either P or V, no problem, but the result won't change. Okay, so that's the thing I need to tell you first. Then now we're going to prove that the S at constant at the temperature becomes 0. Their difference should be 0, not has some value in between. Okay, we want to prove that. So this proof is a little bit tricky that because we want to do it inversely. We are not going to say they equal to 0. The difference is 0. We're not going to prove that. We're going to prove that SO2 minus SO1 equal to something else is impossible. So if we prove that reversely, we want to prove that reversely. Okay, this is a little bit tricky. Okay, so now we assume that if a system with two different initial entropy S1, S2, then when T goes to 0, we'll have different final SO1, SO2. So we prove that not possible. And then, which means that SO1 minus SO1, SO2 minus SO1 equal to 0. Okay, so in fact, we want to prove that this is impossible. Okay, if this is impossible, which also tell us their difference will become 0, is true. Okay, this is what we are going to prove in the next few pages. 好，我们不是有说我们要证明 Nernst theorem 吗？那 Nernst theorem 的意思就是说，两个 entropy 到0K 的时候，它们的差距会缩减为0，大概是这样子。那我们要证明这件事情，要先有跟大家讲3件我们已知的事情。第一件事情是绝对零度无法达到，因为我们刚不是就说总会有一个下限，会比你找到的东西还要下限的状态0K，所以你永远找不到因为总是在你的 lower limit， 在你之下这样子。那第二件事情是 S 等于 S naught 加这个应该没问题吧？那这边有一个这个没问题以后呢，这个 QR 其实是可以被 C over T 所取代，把它做出来的。可是那个 C 呢？这个 C 这边为什么没有 P 或 V 其实没差啦因为你写 CP 或 CV 这条线只是会稍微差距一点，但是答案都是一样的。OK， 所以说我们就把它拿掉了答案不会改变。所以呢，这边你要写 C 或 CP 都可以，只是没意义。好，这是这3件事情我们先讲了。那接下来我们要证明说，这个 S2 跟 S1 到达0的时候，它们的差距会为0，这件事情很难证。那我们这边相反过来变成说， 我们要证明它们有差距，它们不为零的话是不可能的，是不可能的。那这样的话就可以反证说，哦，这个东西是为零的。OK， 那我们就想说，现在有 S2 跟 S1，它们之间有个差距咯。OK， 有个差距了。Next, we're going to do this. So now we have these two curves, okay? But this is the blue state in S2. This is green state and S1. And we found that if we want to match, convert, doing some process, make the green to the blue. Can we do that? Can we see that? Yes. Here, S02 plus this entropy state can be represented by this equation, and this state can be represented by this state equation, right? And then because they are in the same height of the y-axis, so they can be equal. Okay, so which means that if this is true, right? This is true. So which means that you can go through this process to make green to the blue. Okay, so if this is true, this is correct, this is okay, this process is possible, you can make green to the blue state. Okay, however, this state can be arbitrarily chosen. So can we move this, the chosen one, to the SO2? Can we do that? We can do that, right? So if we can do that, this case become here again, but the only difference is that now this is become 0 now because nothing here, right? We can delete that, which means that if you can do that, you can do that, make it T2 equal to 0, 0, 0. So everything's here. So which means that this one is possible. And it also tells us you can make the green part achieve 0 degree. So which means that this gives this one, and then so if SO2 minus SO1 greater than 0, this equation is possible. Okay, this equation is possible, which means that the absolute value can be achieved by this process. So, but absolute 0 temperature is unattainable. So this cannot be the case. So SO2 minus SO1 cannot greater than 0. So we need to reverse that. It must be less than 0. So which means that we need to swap this S1 minus SO1 greater than SO2. Okay, but it's still the same. We can still do exactly the same thing. So which means that SO2 minus SO1 cannot greater than 0, 2. So the only thing left is SO1 equal to SO2. Okay, so that's the reason why they need to be shrink to the point. 好，我知道英文有点难，那我用中文讲一次哈。总之就是说啊，现在有两个状态，一个是绿的状态，一个是蓝的状态。蓝的在 S2 上，S1 在绿在 S1 上。然后啊，它之间是同样的 entropy 的高度哦。好，那蓝色可以写成这样子。绿色可以写成这样的，就我们刚刚之前讲到的。好，那这时候它们既然是相等的高度，好，我们就可以写出一个等号，然后把它就是移动来移动去，我们就会发现它写成这样子。好，那这件事情是什么呢？这件事情就是说，这个 case 如果这个等号是成立的话，表示说你这个动作是可以做到的，这个步骤是可以让绿色跑到蓝色的，这是 OK 的。好，那如果你觉得这 OK 的话，那其实这个 process 是可以
任意的去移动的你可以往上移，往下移。那你总有一天可以移到了一个这个地方，绿色可以跑到蓝色地方去。好，绿色可以跑到蓝色地方去，这个式子会写成什么样子呢？这个式子这边会变成0，因为 T2 等于 T2 prime 等于0嘛，哈，这边等于0了，所以这边等于0了。这边等于0了以后呢，如果你选这个，它跑到这边等于0。好，这式子写在这里。如果这个式子可以成立的话，它可以成立吗？可以吗？我们来看一下哦，它是正的，但是它一定要是负的，加在一起才等于0，才有可能成立，对不对哈？那可能成立的状况下，就表示说它可以跑去0K 了呢，它可以了，那就违反我们的 attemptable 的假设吗？所以说它不能成功，我们不能让它这个东西成功，不然的话我们就违反了物理定律了。所以表示说它不能 SO2 不能大于 SO1。好，所以这不行哦，这不行。所以它既然不能大于 SO1，那我们就换嘛，我们就换 SO1 要大于 SO2。好啦，那我们就重新来一次。SO1 大于 SO2 的话，那就一定是这样子咯。好，我们就重新翻过来一次，结果还是一样啊，我还是一样可以从这边跑到这边来，所以我们的 SO1 不能大于 SO2。哎，你看，刚刚证明它 SO1 不能大于 SO2。我们刚才也证明 SO2 不能大于 SO1，哇，怎么办？所以只有一种方法，就是 SO1 等于 SO2 的时候，这样子的式子才不会成立。OK， 那不会成立了，表示他们就要聚在一起啦。那聚在一起的话，那 OK， so which means that S need to be has 0 differences. Okay, and if we adding with the Planck's statement, it also tells us the finals, this point has no difference, and these points are all at 0. Okay, so we just shrink it and put it 0. Okay, and then you can notice that, yes, we can make green to blue. We can make green to blue by this. Yes, we could do that, but okay, but we will never reach because the step is getting smaller than smaller, and then we cannot reach that. So everything become a puzzle to, I mean, placed together. Okay, that's it. 所以他说，我们刚刚不讲说，不能 SO2 不能大于 SO1，SO1 又不能大于 SO2，所以只能 SO2 等于 SO1，然后让那个式子无法成立，让那个式子无法成立了，就不会跑到 0K 去了。那这时候这两条线就必须要接在一起。那接在一起以后，再加上 Planck's statement 说最后这个 limit to S 会到0点，那就设定为0，我就把这个点接起来以后放到0的地方去。好，所以 S2 跟 S1 它就是一个这样子的线，一直往下走。那往下走的状态下呢，的确啊，我们可以把绿色的状态跑到蓝色状态，可以哦，我们可以这样做。但是事实上就是它的步骤会越来越小，越来越小，越来越小，你永远找不到那个，你永远碰不到那个 lower limit， 就这样。OK， 讲完了。So this is midterm 1's range. Okay, review 3 should be chapter 10, I guess. Okay, so we have another 50 minutes. I will go for work, right? But kinetic part shouldn't be in our midterm 1. It should be in midterm 2. All right. So
Let's continue. Kinetic. For me, I really like kinetic. Okay, kinetic is a little bit reasonable for me. All right. Before we go into statistical thermodynamics, we need to go for we need to explain kinetic first. Okay, because kinetics is kind of the first step for treating the material as atoms or as particles. All right. So firstly, I would like to talk about kinematics. What is kinematics? We typically, if we have mechanics, 力学 mechanics, we typically has certain of scope. Statics means that everything is under the equilibrium, okay, and the force are all stable. But dynamics and kinetics are really similar. They are kind of moving, velocity, and now they are not in equilibrium state. They are kind of moving, fly around. Okay, and kinematics. When I firstly go to University of Oxford, when I study in PhD, actually I didn't know the scope. Okay, I just know some of it. So when my supervisor asked me, do you know the difference between kinematics and kinetics? I didn't know. I thought they are the same, but actually they are not the same. Kinetics means velocity, force, but kinematics is actually describing the motion of points of object, group of object, without consider the force. They just considering the possibility of the point they can reach. So for example, kinematics is in Chinese, we still translate into 动力学, but they are not kinetics 动力学. So they are really similar, but they have fundamental difference. For example, kinematics is that actually study the relative coordinate for the motion of the body. For example, here you have a joint, you have a joint, you have a joint, and the degree of freedom may 180 degree, and here maybe elevate. The maximum elevation should be 10 meters, something like that. So the kinematics means that you are calculating the kind of possible range of this body can reach. It can be here, but it's not possible to be here. Okay, so the kinematics means that the calculating the limitation of the coordinates. It's a local coordinate. This is global coordinates, and this is another local coordinates. Okay, so the kinematics means that the coordinates, how they move, how the body move. Okay, so this is different from kinetic. They are different. OK， 中文讲一下，为什么要特别讲这个？是因为我在去英国留学的时候，我的老师问我说：“哎，你知道 kinematic 跟 kinetic 的差别吗？”我那时候完全不知道这两个是什么东西，我只知道动力学，但是我发现，哎，这两个东西不是都翻译成动力学吗？但实际上不一样哦。Kinetics 就是在讲一个东西受到力以后的速度，飞来飞去这样子，或是跑来跑去这样子的速度会变多少，加速度会变多少 ，OK？ 但是呢 ，kinematics 不是这样子 ，kinematics 其实是它在讲一个指点是怎么样移，它可能移动到哪里。好，所以你可以看到，就是说，像这个地方，它会有3个构件，这3个构件会有不同的 local coordinate，就是 local coordinate local 当地的坐标有全域的坐标跟 local 我翻译一下，全域的坐标跟自己的坐标了哈，所以这边可能会有3个坐标轴，一个是这个手臂的，另外一个手臂的，所以说这有点像是控制的感觉，所以 kinematic 其实是控制的机械系控制那种感觉，就是去学习这个指点怎么移动，相对于某个观测者这种感觉，这是 kinematics。所以你可以去看说它可能运动的轨迹大概是这样，但是我们的 kinetic 是完全不一样的 ，kinetic 就是看它的速度、动能怎样的，所以这两完全不一样。但是中文可能都翻译成动力学，那是要小心一点这样，所以我才在这边特地的讲出来。So, what I'm going to say is that kinetics is really different from kinematics, so please don't mix them up. And so kinetic theory is concerned with the motion of molecule or atom or particle, okay, rather than the force between them. We only talk about the velocity, okay, acceleration, right? OK, 所以我们要讲的是 kinetic，是跟统计力学的入门 ，OK， 然后它是考虑分子跟原子或是颗粒之间的速度跟移动跟加速度。OK, so we will have a fundamental assumption for kinetics. Kinetics. The first one, the first assumption, very important. We are talking about the system that a macroscopic volume contains a large number of molecules. So we are talking about many atoms, many molecules. So you can see that Na it's in 100 kilomole. 100 kilomole. Sorry. 1 kilomole. 1 kilomole containing 6.2 to 6.02 times 10 to 26 molecules. So it's really it's many particles at typical standard temperature pressure, which means that normally we will have 3 times 10 to 25 molecular in each meter cubes. So which means that massive molecules. We assume that many molecules in what we are discussed. Okay, so what is STP? STP here, M equal to 1 kilomole, right? And the temperature here is 273.15 K. And pressure equal to 1 atm equal to 101.3 kPa. Okay. So which means that at STP, volume will be MRT divided by P equal to 10 3 times 8.314 times 273 divided by 1.103 times 10 to 5 equal to 2.4 meters squared. Okay, so you can see that 2.4 meters squared is at STP. Okay, standard temperature pressure. You have such big cube, 2.4 meter cubes, and then containing 1,000 mole, and then averagely each meter cube containing 3 times 10 to 25. So large number. We are not talking about small number of molecules. Okay, this is fundamental assumption 1. Assumption 2 is that the separation of molecule is large compared with molecular dimensions. With the range of intermolecular forces. So which means that at STP, your volume containing such many particles, which means that each particles occupying 30 times 10 to minus 27 meter cubes space. Okay. And if we do cubic root, 开立方根啦，开立方根 cubic root, you can make it 3, you can obtain 3 times 10 to minus 9. Okay, and the diameter of molecule of gas typically times 10 equal to this one. Okay, so which means that the separation of the they are separate. Okay, 10 times of their diameters. Okay, so which means that they are quite free. They are not crowded. Okay, they're quite free. They have plenty of space, so they won't affect each other. Okay, until they touch, until they meet each other. Okay, so in liquid or solid, molecules have nearest neighbors at distance slightly greater than d, so which means that they have neighbors. Okay, so internal forces need to be considered. So liquid and solid are relatively difficult compared to gas, because the gas, their molecules are far away from each other. Okay, so this is a fundamental assumption 2. 好，在进入动力学之前，我们要先有一些假设。我们要假设说，有2个假设。第一个假设，其实有6个假设了哈。第一个假设是，我们假设我们在考虑的系统有非常多的 particle， 非常多的分子。那是不是这样子呢？我们假设是不是真的呢？可以用这样子来去判断哈。就是说我们在1000摩尔的状况下，它在标准的气压跟温度下是22.4的平方公尺，会包含这么多。那我们就可以除看1平方公尺包含了10的25次方克，多不多啊？很多，所以我们的假设还蛮正确的。第二个，我们要假设分子之间距离很远，那怎么样去算呢？我们在22.4里面的空间里面有这么多颗，我们除下它以后就发现一颗平均占据的空间是这样子。那我们把它做一个立方根以后，就变成它们之间的距离的平均，3乘10的负9次方，3乘10的负9次方约等于一般 gas 的直径的10倍，也就是说它们之间非常的松散，它不会是挤在一起的。那但是流体跟固体它就不一样，它们就会有很近的邻居，跟它差不多，就是跟它的直径差不多的距离，所以呢，差不多就是旁边就看到另外一个人，甚至他们很挤，所以我们必须考虑 force 之间的交互作用。那所以就是说，我们这边在他们2颗 particle， 我们这边在2颗 particle 之间还没有遇到之前，我们是不考虑他们的力量。OK， 这就是我们的假设。Okay, so we can, this is the, next week we will have an exam, okay? So I will wish you good luck and thank you. See you next week. All right.